So let's look at problem number 35 from page 196, which is on the second derivative test. So they're giving us a function x cubed minus 3x squared plus 3 and we're asked to find the critical numbers and also use the second derivative test to figure out whether each critical number is going to be the location of a maximum or of a minimum. So first of all, let's find the critical numbers. To do that, we're going to take the derivative and set it equal to 0. So the first derivative is 3x squared minus 6x and that's it. So let's set that equal to 0 and solve for x. I can factor out a 3x. Oops, sorry about that. Come on. The stylus is being disagreeable. Yeah, I know. It got really bad before the end of the session yesterday. So I've got, if I factor out the 3x, I have 3x times x minus 2 equals 0.
So 2.
So either 3x is 0 or x minus 2 is 0. So I'm getting x equals 0 and x equals 2. So those are my two critical numbers.
Yeah.
And now let's apply the second derivative test at each of those. So the first derivative was 3x squared minus 6x. So the second derivative is equal to 6x minus 6. So if I take the second derivative and I plug in 0, that's going to be 6 times 0 minus 6, which is negative 6. That means that the function is concave down, since the second derivative is negative. The function is concave down at that point, which means that this is the location of a relative maximum. Plugging in x equals 2, f double prime of 2 is equal to 6 times 2 minus 6. That's 12 minus 6, which is 6. That's positive. So that means that the graph is concave up at that point. So I'm at a relative minimum.
So you plug the critical numbers back in to see if it's
That's
a relative max.
Specifically, I plugged the critical numbers into the second derivative. Now, if I wanted to know what the maximum value is or the minimum value, then I need to plug back into the original function. So,
okay.
So the maximum would be at 0, comma f of 0, which is at 0, comma, looks like f of 0 is equal to 3 if you use the original function at the top. And the relative minimum has an x coordinate of 2. And to get the y coordinate, I have to plug 2 back into the original function. So that's 8 minus 12 plus 3, negative 4 plus 3. I'm doing it in my head, but I think that's a negative 1. So is that kind of making sense, Christian?
Yeah, so if you plug in a critical number into the second derivative and it's negative, relative max, and if it's a positive, it's a relative min?
That's exactly right.
Okay. And then the other thing was, like, during the homework, it was kind of weird how they wrote the answer. So how would you want us to write it on the test?
So if you wanted to, you could list it as a point. You could say there's a relative maximum at the point 0, 3, sorry, let me change to a pointer here. There's a relative maximum at the point 0, 3, and there's a relative minimum at the point 2, -1. Or you could say the function takes on a relative minimum value of 3 at x equals 0, and it takes on a relative minimum value of -1 at the point 2. So the actual maximum or minimum is the y-coordinate. Oops, does double-clicking make it big? Apparently. The maximum or minimum is the y-coordinate, and you say that the minimum happens at the x-coordinate. Or if you want to, you can just list the point.
Okay. And then I have another question. It was on the homework. This is the last one. Let me find it. 3.3. Hold on. Let me go back to the bookwork thing to see what exactly it was. Quiz material.
Hi, Chuck. I see that you're in the room. Feel free to ask a question. You can either, at the bottom of the screen, there's a place where you can raise your hand. That'll let me know that you got one. Or you can send me a message through the text bubble here. If you click on the little purple arrow at the bottom right, then there's a text bubble, and you click on that, it opens a chat window. You have a quick question, Chris, while Christian's looking for his?
Yeah.
I found it, but he can go first.
Mine's on exam 3. The review.
Okay, hold on just a second while I pull that up. Okay, got it.
Okay. On 1D.
1D.
Yeah, g of x equals the sine x plus cosine x on the interval 0 to 2 pi.
Okay, I'm just writing it down so that I can come back to my regular screen. And this is doing increasing, decreasing, and relative extrema. Awesome, that's a great one. We often don't seem to get enough practice doing the ones with trig functions, so I'm glad to get a question on that. So let me just make a note that this is the exam review. Problem 1D. The function, actually it was called g, it looks like. G of x is sine x plus cosine x.
Mm-hmm.
And we're working on the interval from 0 to 2 pi. So to find the increasing, decreasing, and relative extrema, we need to have the first derivative. So let's calculate g prime. The derivative of sine x is cosine x.
Cosine x minus sine x.
Exactly.
So my problem is when I set that equal to 0, what do I do after that?
Let's do that. So if I set it equal to 0, I can rewrite that as cosine x equals sine x.
Right.
Moving the x to the other side. And if I divide both sides by cosine x, I get a tangent of x is equal to 1. So I need to find all the places between 0 and 2 pi where tangent is equal to 1. Well, remember that tangent is positive in the first quadrant and in the third quadrant. So I'm going to have two answers between 0 and 2 pi. Do you remember where tangent is equal to 1 in the first quadrant?
I'm looking up a unit circle right now.
Hi, Kisva, welcome. Right now we're solving problem 1D from the exam review. Hi, Trick, I see you have a question. I'll answer it as soon as we get to this. Chris, you should be finding pi over 4 on the unit circle is a place where tangent is 1.
I'm bringing it up. Computer's a little slow.
Yeah. And the place in the third quadrant is going to be pi ahead of that. So that's going to be 5 pi over 4. Chuck, let me just check. Did you have a comment about this particular problem, or are you going to ask a different question?
No, I have a question.
Okay, let's hold off on that until we finish this one. So the two places where the derivative is 0 are going to be pi over 4 and 5 pi over 4. So let's do a number line. If the folks who are not in the conversation right now could turn the microphones off, it would reduce the amount of static. So we're going from 0 to 2 pi, and we have two critical numbers. One of them is going to be at pi over 4, and one of them is at 5 pi over 4. And its derivative is equal to 0. And then we get to test intervals. So as usual, we're going to pick a number in each interval and substitute it into the first derivative. So for example, if I pick 0 to the left of pi over 4, my derivative is cosine 0 minus sine of 0, which is 1 minus 0, and that's a positive number. So g prime is positive on the first interval. A number you could pick in that second interval might be pi sitting here in the middle, and we'll pick 2 pi over here. And let me just emphasize, we're plugging each of those into g prime. So I'm taking g prime of 0, g prime of pi, and g prime of 2 pi. If I plug pi into the derivative, cosine x minus sine x, cosine of pi minus sine of pi is negative 1. So this gives me negative 1. So the derivative is negative in the middle. And if I plug 2 pi in, cosine of 2 pi minus sine of 2 pi is positive 1 again. So all of this is coming off of the unit circle. So what I'm getting then is that the derivative is positive and then negative and then positive.
The relative max and then a relative min.
Bingo. So we have a relative max at pi over 4 and then g at pi over 4. So you need to plug pi over 4 back into the original function. And what's happening over here at 5 pi over 4?
You got a relative min.
Bingo. And Christian, this is what you were commenting on earlier. You knew how to read that if the derivative is changing from negative to positive at a critical number, then that means that you're going to have a relative minimum. So 5 pi over 4, and then whatever g of 5 pi over 4 is. You'll figure that out using the unit circle. And the problem also asked about increasing and decreasing. We see that it's increasing from 0 to pi over 4, and also from 5 pi over 4 to 2 pi. And it's decreasing in the middle, where the derivative is negative. Is that good, Chris?
Yeah, so that's good.
My guess is that you are able to do everything down here already, that your main problem was the trig stuff up here. Is that right?
Yeah, it was that I didn't. So when I set it equal to 0, that's where I got stuck. I didn't know what I could do from there.
Yeah.
Yeah.
Did anybody else have a question about this particular problem before we move on to Chuck's question?
I had a similar question.
Well, hang on. Let me grab Chuck, and then we'll circle back to you. Chuck, what was your question?
My question is like on the essential of the chapter 3.6. Like, do we need to find the second RAM for that function?
I'm sorry, I had trouble understanding that. Which question are you asking about? Something on the exam 3 review sheet?
No, no, not the review sheet, like the example you give us for the chapter 3.6.
Okay, so the book, a question from the book?
The example like on the video you show us
Oh,
for
okay.
the chapter, yeah.
So I'm sorry, I'm still having trouble understanding the question. Can you try it one more time, please?
On the chapter 3.6, like on the video on YouTube,
Okay.
you show us like the example example 2. I'm sorry, example 2, like can I write the f is,
Oh, cool.
yeah, equal to is where minus is plus 4 and is minus 1. Yeah, on the video you just find the first gram of f and you didn't find the second gram. So my question is like when we need to find the first second gram.
Um, on the exam, I would do it only if I were asked to. So on the test, I'm not going to be able to have you do an entire function summary sheet just because it would take too long. So what I'm going
Okay.
to do is just ask you to do specific parts of it. So it could be that the only thing that I ask you to do is find concavity. Well, if I ask you to just find concavity, then you're going to have to do the second derivative. But if it's a problem where I just say, I only want you to find increasing, decreasing, and use that to draw the graph, then you won't end up doing the second derivative. But it is true that if you want to do the entire function summary sheet, like you have to do in some of the homework, then you have to go all the way through.
Oh, okay. And how about the range of this function?
In order to find the range, we need to at least find the critical numbers and find the relative maxima and minima. Usually that's enough information to figure it out. I don't have the transcript from the video. Did we actually figure out the graph? Can you remind me or draw what the graph looked like?
Okay.
I see you've got your hand up, Kisva. I've got you next in line.
Okay.
That's awesome. At this point on the left, is that maybe -1, -3?
Oh yeah. Sorry. Yeah, -1 and -3. Yes.
Awesome. So now, once you have the picture like this, it's easy to find the range. Notice that going from bottom to top, this graph goes all the way to -infinity. Man, you're having better luck with the pen than I am. Mine's going crazy. Still going crazy. Come on, behave. Man, I'm kind of hating this. Here we go. So the range starts at -infinity. But then it stops when I get to -3. So the highest point over here on the left is at -3. So I go from -infinity to -3. And I'm going to include the -3, so I'll put a bracket on there. And then union, the range starts again at this point, which has a y-coordinate of 5. I'm going to throw this tablet out the window before the semester is over. Either that or I'm going to figure out how to use it. Starts again at -5, and then goes to positive infinity. I think I'd have better luck just using the trackpad. So negative infinity to -3. Maybe not. And then from, that should be a +5, my mistake, 5 to infinity. Man, okay. So even though that was messy, does that make sense to you, Truk, about finding the
Yeah.
range? Yeah, in order to find the range, you need to know where the relative extrema are, but you don't need anything from the second derivative.
But
Okay,
if
Kisvo,
the graph, I'm sorry.
Go ahead.
Yeah, if the graph it doesn't have like streamer, so how we can find the range?
I don't know how to find the range unless I have the graph.
Oh, okay. So like we based on the graph to find the range, right?
Mhm.
Even like we have a streamer or not.
So even though that on the function summary sheet, that's way up at the top, it's something that you can't usually answer until after you finish finding the relative extrema. So yeah, range is one of the sneakiest things to figure out.
Okay.
Kisvo, let's look at your question. Let's see if I can get this working a little bit better.
My question was just about the relative maxima and the relative extrema. I don't necessarily, I keep getting confused between how to find like the absolute extrema and the relative max and the relative min. I keep getting them confused. I was wondering like I could like, I don't know.
Okay, I'm getting a lot of feedback, so I'm muting everybody except for Kisva. I'm still getting the feedback, but let me make sure that I understand your question. It sounds like what you're saying is that you're having trouble distinguishing between the methods for finding absolute extrema and relative extrema. Is that correct?
Yes, Professor.
Okay, so I'm going to mute you also to see if that gets rid of the feedback. And if you need to follow up with the question, you'll just have to turn your microphone on again. So let's compare absolute extrema to relative extrema. This is a really good question. So for absolute extrema, we are always given a function and we're given a closed interval. So the inputs are you're given a function f of x and you're given a closed interval from a to b. And the method is going to be, first of all, you find the critical numbers. And the critical numbers are going to be anywhere where the first derivative is either 0 or undefined. And then you make a table. And in the table, you're going to list all your critical numbers. And you also have to list your two endpoints, A and B. Now, when I did this in class, I would put the left endpoint first, the right endpoint at the bottom, and I would list the critical numbers in between. The reason is that sometimes you'll end up with a critical number that doesn't sit inside the interval from A to B, in which case you just ignore that. You don't include it on your list. And then you take each of the critical numbers and you substitute it into the original function f. And then you just look down your list. Somewhere on this list, you're going to have a maximum y coordinate, and somewhere you'll have a minimum y coordinate. And those are going to be your absolute maximum and your absolute minimum. Remember that the absolute maximum and minimum are the y coordinates. So as I was mentioning to Christian earlier, you would say, for example, if I had a biggest value of 12, and that happened when x was equal to 2, I'd say that the function takes on the maximum value of 12 at x equals 2. So that's absolute extrema. For relative extrema, the method is different. You still start by finding the critical numbers. But then, instead of looking for absolute extrema, you're going to try to figure out whether each of these critical numbers might be a relative max or a relative min. And there are two ways to classify them as relative max or relative min. One is the first derivative test, and the other one is the second derivative test. The first derivative test involves writing a number line for f prime, where you put all your critical numbers on here, and then you test the intervals to see whether the derivative is positive or negative on each interval. So for example, I'm saying the derivative is positive, then negative, then positive. If that were the case, at this point, since the derivative is changing from positive to negative, that means that the function is increasing and then decreasing, which means that the critical number would be a relative max. It'd be the location of relative max. On the other hand, if the first derivative changes from negative to positive, then that means that the function is decreasing and then increasing, which means that you'd be at a relative min. The second derivative test is a little bit different. In the second derivative test, you still find all the critical numbers, but then you substitute into the second derivative. If the second derivative is positive, then that means that the graph is concave up at the critical number. And if the graph is concave up, then that means that critical number has to be a relative min, because it would be at the bottom of the parabola. Whereas if the second derivative is negative, then that would indicate that the graph is concave down, which means that your critical number is a relative max. So that's kind of an overview of it, Kisva. Are there some specific questions or problems that you wanted to look at, or did that clear it up?
No, that cleared it up. Thank you.
Awesome. Christian, you've been very patient. Did you find that other question you wanted to ask?
Yeah, it was number 41 on 3.3 or page 187.
Cool,
It's
thanks for
kind
the
of
page
similar
number.
to,
Found it. It's the one with x minus 2 sine x?
yeah, it was similar to Christopher's question. Like once you
Yeah.
set it to 0, what do you do?
I'm happy to work examples with the trig functions, because like I said, we don't seem to get enough practice. So this is 41 on page 187.
Yep.
So the function we're given is x minus 2 sine x. And we're trying to find the open intervals where it's increasing, decreasing, and we're also trying to find relative extrema, find and classify using the first derivative test. So first of all, let's take the derivative. The first derivative will be 1 minus 2 cosine x. There's no place where this is undefined, so I can find all my critical numbers by setting this equal to 0.
Wait, you don't take the derivative of, I thought it was like 2 times sine x.
It is. So I use the constant multiple rule, so the derivative will be 2 times the derivative of sine of x.
Oh, yeah, okay.
And now, Chris, you might notice that I'm going to use a similar technique to what I did with the question you asked. I'm going to move the 2 cosine x to the other side, so I have 1 equals 2 cosine x. And then I'll divide both sides by 2. So I have a half equals cosine x. One part of the problem I didn't write down is that we're only looking on the open interval from 0 to 2 pi. So I need to find the places where cosine is equal to 1/2 between 0 and 2 pi. Cosine's positive in the first quadrant and in the second quadrant. Oops, sorry. Cosine's positive in the first quadrant and in the fourth quadrant. So I need to find where cosine is equal to 1/2 up here and then also down in the fourth quadrant. So did you guys find your unit circle? Do you know where that's happening?
Pi over 3?
Pi over 3 is indeed the place in the first quadrant.
And the fourth quadrant's 5 pi over 3.
Awesome. Thank you, Kisva. So I've got two critical numbers at pi over 3 and 5 pi over 3. And then this next part is going to look a lot like Chris's question. I'll draw my number line, only going from 0 to 2 pi. And this is for f prime. I'll mark pi over 3 and 5 pi over 3. And, oh, drat, I was doing so well. The first derivative is 0 at each of those points. So let's see, we need to test intervals now. Obviously, in the first interval, I can test 0. In the second one, I can test pi. And in the third one, 2 pi. So I need to plug those into f prime and see whether I'm getting something which is positive or something negative. So f prime of 0 is 1 minus 2 cosine 0, which is 1 minus 2, or negative 1. So the derivative is negative there. F prime of pi is 1 minus 2 cosine pi. Cosine pi is negative 1, so this is 1 plus 2, or 3. So that means that my derivative is positive in the middle. And at 2 pi, cosine is 1 again, so that's giving me negative 1 as my derivative. And then we need to do the increasing, decreasing, and the critical numbers. So the function will be increasing when the derivative is positive, which is from pi over 3 to 5 pi over 3. And it's decreasing when the derivative is negative, which is 0 to pi over 3, and also 5 pi over 3 to 2 pi. And let's talk about what's happening at the critical numbers. At pi over 3, am I looking at a relative maximum or a relative minimum?
A relative minimum?
That's right, because the derivative is changing from negative to positive, which means the function is decreasing and then increasing. So I have a relative min at pi over 3. And to get the y-coordinate, which is the minimum, I'd have to plug that pi over 3 back into the original function. And then what's happening over at 5 pi over 3, max or min?
Maximum?
That's right. Because the derivative is changing from positive to negative. And once again, to get the y-coordinate, I'd have to plug 5 pi over 3 into the original function. Question?
And it does look like a sine graph.
Similar. Actually, I was just grabbing Desmos. If you have it handy, you might want to do it too. Let's graph the original function, x minus 2 sine of x.
Oh, well.
So, tell you what, I am just going to switch to the camera for a moment. Got to remember how to do that. I think I turned the whiteboard off. There we go. I can't see myself, but can you see the screen there? Are you getting a graph that looks something like this?
Yep.
Now we only care about the part between 0 and 2 pi, so let me kind of click those. You probably can't read mine, but notice that that minimum is happening at pi over 3 comma a certain number. That's going to be the number you get if you plug pi over 3 into the original function f. And this maximum, again, I don't know if you can read it, but the x-coordinate is 5 pi over 3, and the y-coordinate is going to be whatever you plug in. So this kind of confirms what we were expecting. We were expecting a relative minimum at pi over 3 and a relative maximum at 5 pi over 3.
Mhm.
That was a great question.
So if we already know, based on looking at the number line, what's going to be relative max and min, then what's the point of taking the second derivative test?
Something that I mentioned in class is that in order to use the first derivative test, you have to know where all the critical numbers are, because you need to make sure that you're testing the intervals in between the critical numbers. Whereas if you want to use the second derivative test, it's possible to do the test just at the critical number you're interested in without knowing where all the rest of them are. So if you have a function that has lots of critical numbers and it's hard to solve for all of them, then it could be more efficient to use the second derivative test instead of the first.
Okay. So if you're given like a large polynomial.
That is exactly the situation that I have in mind. If you have a polynomial that has lots of solutions and you just don't have time or you're not interested in finding all of them, you just want to know the behavior of one particular solution. Hi, Ismail. I see that you come in the room.
All right. Thank you.
Folks, oh, Ismail, you got your microphone on. You can either ask me a question. Notice there's an icon at the bottom to raise your hand if you need to get my attention and I'm talking to somebody else. Guess what? You got a question?
Yeah, Professor, on homework 3.4, could you do question 23, please?
Sure, let's look at that. 3.4.23?
Yes, sir.
Oh, yikes. Maybe I said yes too soon. So this is problem 21 from page 196. The function is equal to x times x minus 4 cubed.
Professor, it was question 23.
Drat, I was trying to give myself an easier one.
Oh, sorry.
So that one is x times the square root of x plus 3. Okay. And the problem is it wants us to find the points of inflection and also talk about concavity. So this is one where we have to take the second derivative. I think Truk was asking earlier about when to take second derivatives. If we're told to do concavity and points of inflection, we've got to do second derivatives. So let us rewrite this as x times x plus 3 to the 1/2 power. And then we're going to have to take two derivatives using the product rule and also the chain rule. So let's take the first derivative. Using the product rule, it'll be the derivative of the first times the second plus the first times the derivative of the second. And for the derivative of the second, I have to use the chain rule. So I'll have 1/2 times x plus 3 to the negative 1/2 times the derivative of the inside, which is 1. So what I have so far is x plus 3 to the 1/2 plus 1/2 of x times x plus 3 to the negative 1/2. Can somebody confirm that that looks right before I go any further? I don't want to make a mistake in the first derivative before I take the second. Is that looking good?
Yes.
Yes, sir.
Okay, good. Now let's take another derivative. The first one's easy. That one only involves the chain rule. So I get 1/2 times x plus 3 to the negative 1/2 times the derivative of the inside, which is 1, plus, and now for the second part, I do need to use the product rule again. So I'm going to apply the product rule, letting u be the 1/2 x and letting v the x plus 3 to the negative 1/2. So using chain product rule, it'll be the derivative of the first, which is 1/2, times the second, plus the first times the derivative of the second. And here's the chain rule again. The derivative of x plus 3 to the negative 1/2 is going to be negative 1/2 times x plus 3 to the negative 3/2 times the derivative of the inside, which is 1. And now let's clean that up a little bit. These first two terms are alike. I have half x plus 3 to the negative 1/2 plus another half x plus 3 to the negative 1/2. So if I combine those, I get x plus 3 to the 1/2. And the second one, I can multiply 1/2 times a negative 1/2 to get negative 1/4 times the x times x plus 3 to the negative 3/2 power. So let's see what this looks like. This is 1 over x plus 3 to the 1/2 minus, in this fraction, I've got a 4 in the denominator. I have x plus 3 to the 3/2 in the denominator and an x in the numerator. So let's get a common denominator. I need a 4 on the bottom, so I'm going to multiply by 4 over 4. But also if I look at my exponents, I have a 1/2 exponent here and a 3/2 exponent here. So to get the same power of x plus 3, I need to multiply by another x plus 3 on the top and on the bottom. Because x plus 3 to the first times x plus 3 to the 1/2 is x plus 3 to the 1/2, which is the same as 3/2. So let's see what we get now. My common denominator is 4 times x plus 3 to the 3/2 and on top, from the first fraction, I have 4 times x plus 3, which is 4x plus 12, minus an x from the second one. So that's 3x plus 12 over 4 times x plus 3 to the 3/2. That was a lot of work. But does that second derivative look right before I go any further?
Yeah, it looks right.
Okay. I need to copy that down because I can't clear just part of the screen. When I erase the screen, the whole thing disappears. So you might want to make a note of that first derivative also before I clear the screen. Okay, everybody got it? Here we go. So what we found for f double prime is, Mel, I'll be with you right after I finish this one, is equal to 3x plus 12 over 4 times x plus 3 to the 3/2 power. So the possible points of inflection are going to be any places where the second derivative is either 0 or undefined. Now notice that f double prime is undefined when x equals -3, because that gives us a 0 in the denominator. And f double prime equals 0 when the numerator is 0. So that's 3x plus 12 equals 0. So that's when x equals -4. Hang on just a second. Okay, good. So when I draw my number line for f double prime, I have 2 points that I'm interested in. One of those is going to be when x is -4, and one is when x equals -3. At -4, the second derivative is 0. At -3, I'm just going to write the letter u for undefined. Now, -3 is actually not the location of an asymptote, because if you look at the original function, ooh, there's something I didn't know. I'm just noticing about the original function. I have x times the square root of x plus 3. Notice that the function is defined -3. When I plug in -3, I just get 0. Oh,
Sir, a question.
yes.
Is -4 in the domain? Because
It
in
is
the
not. It's
so
not in the domain.
we wouldn't include -4 in on the number line, would we?
That's right. That's what I'm puzzling about. So I'm wondering whether I took my derivative incorrectly or whether that's really what happens. I'm sure there's some times when you guys doubt yourselves too. So what I'm going to do is I'm going to cheat for a moment. I'm going to draw the graph. And if the graph is contradicting what I'm seeing, I need to go back and check my derivatives. Nope. This is good to go. We've done everything right. So as Chris is noticing here, the domain is only going to be when x plus 3 is positive, which means that x has to be greater than or equal to 0. X has to be bigger than or equal to -3. When I gave you the instructions on how to do problems like this, I told you to check the domain first thing, and I didn't do that myself. So actually, none of this is of interest to us because it's not in the domain. Good catch, Chris. So really then, we only have one interval to check. There are no critical points at all, so we only need to check the interval from -3 to infinity. So let's maybe plug in 0. If we take f double prime of 0, then from up here, we see that gives us 12 over 4 times 3 to the 3/2 power. And I don't really care what number that is. All I care about is the fact that that's a positive number, which tells us that the function is concave up from -3 to infinity. And since there's no place where the concavity is changing, that means that there are going to be no points of inflection. Now, when I was cheating, can y'all see my camera without me leaving the whiteboard screen? Can y'all see that or not?
Yes.
Yes,
So,
sir.
yep. So here, you can see people trying to show you stuff. You can see that the graph, first of all, it has a domain from -3 to infinity, which is what Chris's catch was. Also notice that the function is concave up on its entire domain. So definitely no points of infinity or points of inflection, and concave up forever. Wow, that was an awesome question. Oh, and Kisva logged out before seeing the end of it. Okay, Ismail, you got a question?
Yeah, Professor, I was wondering, how are we going to do the tests?
So for the first test next week, the best thing that I feel like I can come up with is to have you guys test during regular class time. I'm going to post the test on Blackboard and make it accessible to you 30 minutes before class usually starts. so that you can download it and get started. And I'm going to leave it open for about 25 minutes after class would typically end. And during that time, you can scan it and post it to Blackboard just like you did with the homework yesterday. So it's going to be on the honor system. I'm going to ask you to do it using the same things that are allowed on regular tests. So you can use the scientific calculator, but no books, notes, websites, apps, and so forth. So I guess the short answer to your question is it's going to be a timed take-home test that you'll take on the honor system. You'll download it and upload it to Blackboard. Your class normally meets until, what time is your class usually end? 1:35?
Yeah, it ends at 1:35, and I believe it starts 11:45. I don't know.
Right.
Something
So
like that.
I'll make the test available to you at 11:15, and I'll leave the Blackboard site open, or the submission site open until 2 o'clock. So you'll have that 25 minutes to maybe finish the test up, but then also to scan it and upload it to Blackboard like you did the homework.
Okay, thank you.
Sure. All right, so what other things do we want to talk about? We've still got plenty of time. Chris.
Yes, sir. Exam 3, just a quick question on 1A.
This is the review sheet.
Yes, for the review sheet.
Okay, I see that one.
1A. You have a relative minimum at in the answer sheet at F0 equals 0. But on my, I have 0 as undefined. So how do we have a minimum? I thought they had to be, it had to be zeroed out.
That's an awesome question. Remember that the critical numbers are the places where the derivative is 0 or undefined. And at 0, the derivative is undefined, but it is part of the domain of the original function. If I plug 0 into f, I get 0 out. So 0 is in the domain of f, even though it's not in the domain of f prime.
Okay.
Does that make sense?
Yes, sir.
So this is another one where it's kind of instructive to look at the graph. Let me see if I can get that fairly quickly.
I think it looked like an M. I remember I looked it up like last night.
Oh, good job. So let's see, 16 minus x squared, 16 minus x squared. I'm just doing this for the benefit of the other folks. You're right, it does. If I change the color, it would look like the golden arches. You guys see that? It does look like an M. So notice that there are 2 points symmetrically placed where the derivative is equal to 0. Let's see. According to Desmos, where am I? There it is. According to Desmos, those are happening at -1/2 and +1/2. Notice that 0 is also a critical point, but that point is called a cusp. It's not a place where the derivative is equal to 0, but it's a place where the derivative is undefined. And cusps are also places where you can have relative extrema. And in this picture, we can see that that's a relative minimum. It's lower than any of the other points in the neighborhood. Good question, Chris. Guess I'm sorry you're having trouble connecting. I keep getting pop-up messages saying that my connection speed is slow, that you guys might not be getting clear video.
I'm getting clear video and everything else. I'm done with my questions, so I'm gonna mute you, but I'm gonna stay on and listen to if anybody else has anything.
Cool. Everybody else is welcome to do the same. Like if at some point we run out of questions, then feel free to just leave this on in the background so that you can see whether anybody else rings in.
Professor, so on 3.4, could you do like question 53 where we sketch the graph? It's on page 197.
Okay, I'm on 197. And which problem are you asking about? 54?
53.
53. Awesome. Yeah, I'm trying to remember, but we might actually have a question like this on the test. I'm not positive, so it's a good one. So I'm going to mute you again, but you can turn the microphone back on if you need clarification. So let's first of all just copy down all the information that we're given and then see if we can get a picture. F of 0 and f of 2 are both equal to 0. So in terms of the graph, that tells us that we have x-intercepts there. We know that f prime is positive when x is less than 1. We know that f prime of 1 is 0. We know that f prime is negative when x is bigger than 1. And we know that f double prime is always negative. So something that I think is a really good idea is to capture all of this first derivative information on a number line, because we're way more used to looking at that information using a number line than just as inequalities. So if we draw a number line for f prime, then I know that f prime of 1 is 0. If x is less than 1, the first derivative is positive, so I could put a plus here. And f prime is negative when x is bigger than 1. So notice that that number line captures all of the information that's in that red box. Well, wow, I can draw a picture of this. The function is increasing until I get to 1, and then is decreasing afterward. Now down here we were told that the second derivative is negative, which means that the graph is concave down, and the graph that I just drew, kind of an upside down parabola, satisfies that. The only part that I haven't drawn is that f of 0 and f of 2 should both equal 0. So maybe I can put the axes in. I have to have an x-intercept at 0 and an x-intercept at 2. And then I have to have a relative maximum at 1. So let's make sure that this satisfies all the conditions that were given. F of 0 and f of 2 are both 0. Well, I missed a little bit, but there's f of 0 and f of 2. Those are both 0. The derivative is positive when x is less than 1, so that means that the graph is increasing until I get to 1. F prime of 1 is 0, so the tangent line is horizontal here. And f prime is less than 0 when x is bigger than 1, so the function is decreasing. That matches up with our idea of what happens with the first derivative test. If the derivative is positive and then 0 and then negative, then that means that I have a relative max. And then f double prime is 0 means the graph is concave down. So that looks good. Gisva?
I'm sorry, I have one question on 3.4.
Okay.
It's question 30.
Is this question good? Problem number 53?
Yes, sir. Thank you.
Okay, let me clear that out. And Gisva, did you say section 3.4?
And the question is 37. It's on page 196.
Got it. That's the one with the x to the 4 minus 4x cubed?
Yes, sir.
Cool. And I'm just looking back at the instructions. It's saying to find the relative extrema and apply, find out whether they're maxima or minimum in the second derivative test. Cool, so we're gonna do this. I don't know whether you saw at the beginning, I also did problem number 35. So if you need to see a second example, then later on when I post the video, you'll be able to look near the beginning of the session, and number 35 will be in the notes also. But here's number 37 from page 196. So the first step is to find the critical numbers, and we do that by taking the first derivative. Oops. Sorry, hang on a second. My stylus is frozen up. Still not responding. Let me track that. Oh boy, here we go. Sorry, give me a second. Oh, mouse can do some crazy stuff. Scribble, scribble, scribble. Oops. Sorry about that. Technical difficulties. Okay, I'm back. So first of all, we need to take the first derivative so we can find the critical numbers. The first derivative is going to be 4x cubed minus 12x squared. And the critical numbers are going to be the places where that's 0 or undefined. And of course, there's no place where it's equal to 0. So I only need, or sorry, no place where it's undefined. So I only need to look at the places where it's equal to 0. So let's set that equal to 0 and solve. I'll either have x squared equals 0, which means that x is 0, or I have that x is 3. So these are my two critical numbers. So now to use the second derivative test, I need to take the second derivative and plug each of those critical numbers in. And something unfortunate is going to happen in this one. Taking the second derivative, I get 12x squared minus 24x. And then I need to substitute each critical number in. So let's look first at what happens at 3. F double prime of 3 is 12 times 3 squared minus 24 times 3. Let me grab my calculator. That's 12 times 9 minus 24 times 3. That's 36, which is positive. So since the second derivative is positive at that critical number, that means that I'm at a relative min. So there's a relative min at x equals 3. So to find what that minimum value is, I would need to substitute back into the original function, which I'll let you do. So that relative minimum value would be f of 3 using that original function x to the fourth minus 4x cubed plus 2. Now there's a reason that I didn't do 0 first, because look what happens at 0. When you take the second derivative and plug 0 in, you get 12 times 0 squared is 24 times 0, which is 0. And that's one of the bad things about the second derivative test. If the second derivative is 0, that means that the test is inconclusive. There's not enough information to figure out using the second derivative whether you're at a maximum or a minimum. So when that happens, what you have to do is back up and use the first derivative test instead. So we need to go back and look at f prime. I'll put my two critical numbers on here, 0 and 3. I already know what happens at 3. I know that 3 is a relative minimum, but I need to test around 0 to figure out what happens there. So I'm going to go back to f prime, which is here, and I have to test intervals to the left and right of 0. If I plug in -1, f prime of -1 is -4 minus 12, and that's a negative number. And if I plug 1 into the first derivative, f prime of 1 is 4 minus 12. That's negative also. So since the derivative is negative and then negative again, that means that there's neither a max nor a min at 0. Now, we could not have predicted that just because the second derivative is 0. If the second derivative is 0, really anything can happen. So we don't know that necessarily that it's going to be neither. Let's look at the graph real quick before we move to another question.
Yes, sir. 3 is 0 or undefined.
At 3, the derivative was 0 at both of those points. So let's see, the original one was x to the 4th minus 4x squared plus 2. Well, drat, that's not agreeing with my picture, so I must have made a mistake. So let's look at the picture and then go back and find the mistake. Oops, I think my mistake is I typed it in wrong. Oh, it's because it's minus 4x cubed. That's my mistake. There we go. So here's the graph I'm getting. Hopefully you're looking at something similar. Notice over there at x equals 2, or sorry, at x equals 3, I really do have a relative minimum. And in fact, from the picture, we can see that it's an absolute minimum. But at 0, you can see that the graph flattens out and then goes down again. So the function is decreasing, and then it levels out, and then it decreases some more. So at 0, I don't have a maximum or a minimum. Does that answer your question, Kisva?
Yeah, it does. Thank you.
Awesome. What other questions do you guys have?
Professor, you know how you like give us a list of all the things that are going to be on the test? I was wondering if you already gave a list for like exam 3.
I believe that I did. If you check on Blackboard in the week 11 study plan, I think I give you a description of the exam.
Oh,
I don't know whether,
all right.
I don't know whether you can look at that at the same time you have this window open.
Oh, okay. Thank you.
I'm still trying to remember whether I posted that. I'm pretty sure I did. What else do you guys have?
Well, so you also have the review and the review notes accessible, so that should cover everything, right?
Yes.
Okay.
And I can't remember which day it is, but in the study plan, I give you the time that the relay is going to be available, and the relay is going to be another one. Instead of doing it in class for 2 hours, I'm going to give it to you at least a day ahead of time, and you'll have about a day or maybe more to work out the relay and then post your solutions to Blackboard. And I'll give you bonus points on it. Pardon?
That's this Friday or is it next Friday?
Let me look it up.
I didn't check the calendar. I didn't see the exact date on the weekly study plan.
Yeah, let me see. I might not have mentioned it, but I can check. Yeah, the exam 2 bonus point relay is available on Blackboard from midnight a.m. on Friday, March 27th until 11:45 a.m. on Monday the 30th. So on Friday the 27th, it's going to become available, and you'll have the weekend to do it. And
so the test is Monday, right, Professor? Sorry.
yeah, go ahead.
So the test is on Monday, and we get like from 11:25 till 1 a.m. 1
No, that's not correct. The test is going to be on Wednesday.
Okay.
Isn't that what it says on the calendar?
Thought it said Monday, but never mind.
Oh, drat. I just noticed a typo in here. It says Thursday, and that's definitely not right. Let me correct that right now. Our class meets Monday, Wednesday, not Tuesday, Thursday. Let's see. There we go. So that's fixed in class. So yeah, Monday's going to be a review session. I'm going to try to make it similar to what we normally do in class. The only thing is that you will be doing the relay at home. It'll be due at 11:45, and then from 11:45 to 1, I'll be in a chat session like this so that I can answer your questions. What I did with my Calculus 3 class, and they're taking their test this week, is after the review session, or after everybody had turned in their bonus point relay, I asked folks to share what their answers were on the discussion board. So I don't want you to share answers on the discussion board before it's due, but after it's due, that'd be an awesome time to share and make sure that everybody was doing the problems correctly. And in fact, I was really lucky in that one student pretty much aced the bonus point relay. So I just took her solution, with her permission, I took her solutions and posted them to Blackboard. And I'll be glad to do the same thing for you guys. If as I'm skimming through those, I notice that somebody's done it, they've aced it, then I'll be happy to post the solutions to Blackboard after everybody turns theirs in, after the deadline. Hang on just a second. I see that somebody's raised their hand. I'll be right with you. Having the wrong day listed in the study plan is a bad mistake. I want to fix it while I am thinking about it. Oh, somebody raised their hand and they must have put it back down again. I'm back if you need to ask a question.
Yeah, my question was, when are we gonna do the relay question, or when is it due?
I'm going to make it available to you on Friday the 27th, which I guess is this Friday, and it's going to be due at 11:45 on Monday. And you'll upload it to Blackboard just like you did the homework.
Okay, thank you.
Oh, Trent, I just noticed that you logged in. I didn't see you there before. Let me know if you've got a question. You can either raise your hand by clicking on the icon at the bottom, or there's a purple arrow at the bottom right of the screen. If you click on that, you can get into a chat window and send me a message. So if you guys are running out of questions, I'm going to leave the session open. So if you want to, you can just stay in the room. Just keep your ear open to see if anybody else logs in and I start working problems again. If you don't have questions, I've got some other stuff I can work on, like grading your homework, and I'll just be available until 1 o'clock. So I'll be here until 1 o'clock if you've got questions. But if you don't, oh, there you are, Ismail. What you got?
So bookwork 7 was due yesterday, right?
Mm-hmm.
And we can't submit it now. Is that correct?
Yeah.
Okay.
Why? Do you have it
Yeah,
down?
I started working on it, but I didn't complete it because I had work. But
How
it's
much
all good.
how much of it had you already finished?
Maybe like 2 questions.
So yeah, that wouldn't make very much difference.
Yeah. All right.
Yeah, yeah. I'm going to be a little bit tougher on deadlines. I did
Okay.
give an extra day on this one.
Yeah, I know.
Yeah, sorry about that.
It's all good.
Okay, I'm going to mute my video and audio for a minute now. So I'm just going to work on some other stuff. But bring in if you have a question. I'll get a if you click on the little icon that says raise hand, I'll hear the audio signal. Hi, Julie. Got a question? Julie, you raised your hand?
Oh, hello?
Yeah.
Okay. Sorry about that. Okay, so I need help on number 5, the honors homework number 3, the
Okay.
grade homework.
Let's see.
It was number 5 and 6 that were like the hardest ones that you said on the homework.
Okay, so let me see if I can pull that up. Hold on a second.
Okay.
So which honors homework was it? Graded homework 5?
3, number
Oh,
3.
graded homework 3.
Yeah, and number 5 and 6.
Okay, were you able to do part A on problem 5, where you find 2 times P?
I'm confused on the whole question. I don't know how it's like what I'm supposed to, because it gives me 2p, but I'm not sure how to solve it.
Okay, so I can go through some of this. Have you had a chance to look at the videos that I've posted for the honors project yet? No, you haven't, because you're not in
Yeah,
that.
because
So
yes.
what I think the number one thing I need to do is I need to share that playlist with you.
Okay, and
So
I'll share with Chriswell as well.
yes.
Yes.
So I'm just trying to figure out the easiest way to do that.
Okay.
And that's going to be to send you an email. And since
Yes.
nobody else is asking questions now, I think I can do that right now. So just hang with
Okay.
me while I look that up.
Okay.
So let's see. Honors video. Study.
So are those videos, do they correlate with the honors problem?
They do. They're not problem by problem, but they cover pretty much how to add points, duplicate points, and everything. So I even backed up
Okay.
a couple of homeworks. So it's basically if you would come to office hours and I'd just worked a bunch of examples for you.
Oh, okay.
So I'm just trying to figure out. Oh, here it is. I should just go to the playlist. It's open. So it's a YouTube playlist, kind of like what I'm doing for your class notes.
Uh-huh.
And
So also with our honors project, how is this going to work? Because I know it's like presentation based. Is that correct?
yes. So hold on just a second.
Okay.
That's weird. There it is. So I just a link to the honors video, so let me know if you get it. Hopefully you will.
Okay. I'm checking right now.
Cool, I just sent it.
Okay.
Okay, so the idea behind how it's going to work is I'm going to pick a selection of problems either from the earlier homeworks or similar to those on earlier homeworks. And I'm hoping to have like maybe 8 or 10 questions. And then the presentation part is we're gonna roll a die, I guess virtually. It's like, hey Siri, pick a number between 1 and 8.
Okay.
The random number is 8. So we'll do something like that, and that means that you'll just work problem number 8 for me. So what we'll do is sometime over the next few weeks, we'll set up a one-on-one session like this one, and we'll pick a problem for
Okay.
you to do and you'll work it. So you'll have the problems in advance so you can work all of them out ahead of time. But just live, I'll ask you to work
Okay.
one of the problems out for me, maybe using the whiteboard here and collaborate.
Okay. 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 That sounds like a plan. And I got your email, by the way.
Terrific. Hopefully Kisva gets it and understands it. I'm sorry I forgot to send that to you.
Oh,
I'm
okay. That's
hoping
fine.
I'm hoping that you're going to find that really helpful. And
Yes. Okay.
I've got your homework in queue. You sent it to me over spring break, and I was not looking at homework during spring break. But it's on my list to do today or tomorrow to look at those homeworks that you
Okay.
sent.
Okay. Okay. Thank you, Professor. I'll take a look at those videos and
Sure.
see.
And show up in office hours again if you need me to clarify. But I think that they're going to help with the one questions you're asking about.
Okay. Okay. Thank you.
Sure.
You have a nice day.
You too. Hey, Chris, what you got?
On 2C, sir, in the answers, you got, where's it at? Hold on, getting there.
Nope.
Negative 112
Hang on
over.
just a second. I closed that file out just a few minutes ago,
Okay.
but I can find it. 2C, that's the one about concavity?
Yes, sir.
Okay, gotcha.
I think on the points of inflection where you have, I got negative 104 over 27. That's the only difference I have from that whole problem.
Negative 104 over 27. So that would just have to do with plugging 2/3 into the original function.
Mhm.
So let's just work that out. Oh, that's disgusting. I don't want to plug 2/3 into that.
Yeah, I did it all right here. It's all in the calculator. I think I'm right. You might. I doubt you can see that.
Nah. Oh wait. I think I can expand your pic. Oh, show it to me again.
Okay. Well, I did it step by step, so it's not one of those big calculators. 1 second. Let me get down to that.
You're getting negative 1/4 over 27.
Yes, sir. Let me. I can redo it. 1 second. Oh, yeah. Okay. It's 3x to the 4.
So what, I think it'll be easier for me to type this on my computer than to type it in my calculator. So I'll work it along with you.
Okay. So 2/3 to the 4th, 16 over 81 times, where we at? Times 3 equals to 16 over 27.
So we're taking 2/3 and plugging it into 3x to the 4th plus 2x cubed minus 12x squared plus 3x minus 2. All right. You work on it, I'll work on it, and we'll see whether we meet in the middle.
Over 81 times 3, 16 over 27, and 2/3 cubed. Oh, I know what I did. Never mind. You might. I found it.
Okay.
Yeah,
Cool.
I got the 2/3 cubed, and then I multiplied by 3 instead of 2.
Oh man. I know the feeling. This seems to be happening to me in the middle of or I realized that I made a mistake like 5 minutes ago in a video. It's like, oh, what do I do? Do I have to record the whole thing over again?
2 divided by 3, 2 to the 4 equals times 2. That's what it is. 16 over 27.
Good.
Cool. Yep, I got what you got.
Awesome.
Yeah.
That's a good feeling.
Yeah. Whoopsies. All right, chiming back out. Thank you, sir.
Cool.